Okay, so we were looking at different ways to parameterize things. And so here's another one I wanted to give you. So here's another example. I think that last one I called an example. Yes, I did. That was example 5. Okay, so we're going to start with example 6. This one's a tricky one. Okay, so X is equal to cosh of T and Y is sinh of T. So just in case you don't know, these are what the hyperbolic cosine, and hyperbolic sine. So I want to try to figure out what is the Cartesian equation for this and the graph. Okay, so we twofold, finding the Cartesian equation and finding the graph. Okay, so we need to use the rule that if you take the cosh squared of T and subtract the sinh squared of T, you will get 1. So let's use that rule. So the cosh squared of T is just X squared. And the sinh squared of T is just Y squared. Okay. So therefore, this just gives me 1. Now, X squared minus Y squared equals 1 is a conic structure. It is a hyperbola. Now it opens up in the X direction because X comes first. All right. And I need to give you another piece of information. I also want to tell you that T is between, nope, that's all I'm going to give you. And we're assuming T is a real number, of course. Okay, so that's all I'm going to give you. So if you graph this hyperbola, you would get something that looks like this. And then you would go on to the next problem. And I would say to you, oh, I'm sorry, you guys, there's a problem with that. And the problem is that the cosh of T is always positive. So if T is a real number, which it is, then the cosh of T is always greater than, it's actually greater than or equal to 1. Okay. So therefore, that means that X is greater than or equal to 1. So that means that this side of the curve actually doesn't exist. So the only part of this parameterization, and that's what's tricky, is that. Okay, now the question is, which direction does it go in? So you have to see that Y is the sinh, and that increases in T. So therefore, as T increases, the sinh increases. So it is traversed in that direction. Okay. How can we actually create parameterizations? All right, so let's find a parameterization for a Cartesian curve. Now, some of these are easy. So given X squared plus Y squared is equal to 1, we can let X equal the cosine of T and let Y equal the sine of T. and say t goes between 0 and 2 pi. That'll give me the whole circle. Another one, how about x squared plus y squared is equal to a squared? Okay. Well, I can let x equal a cosine t, let y equal a sine t, 0 less than equal to t less than equal to 2 pi. So that's two easy ways to parameterize circles. Here's another curve. X squared over a squared plus y squared over b squared is 1. So what is that? What's that conic section? I went from a circle to what? Anybody know what that is? Okay, that's an ellipse. So I can let x equal a cosine t and y equal b sine t, 0 less than equal to t less than equal to 2 pi. And that'll trace out the whole ellipse. Okay, here's an easy one. Y is equal to mx plus b. What is that?
It's just a line.
It's just a line, okay? So I can let x be t, y can be m times t plus b, and t can be any real number. So I can parameterize that way. Okay, one more. Y is equal to x squared. So this is a parabola. So I can let x equal t and y equal t squared. All right. Or I can let x equal the square root of t and y equal t to the 4th. They'll both give me the same parameterization. Okay. Let x equal t cubed and y equal t squared. No, y would equal t to the 6th. Is that right? Something about that seems weird to me. Something about the second one doesn't seem right. If x is t cubed, then y is t squared. So this one should just be t. Okay. Right. So this one actually travels faster. and this one will travel slower. Okay, so those are different ways to do that. All right, so the last thing for this section is to find the actual parameterization for a cycloid. Okay, so here's a cycloid. All right, so what is a cycloid? All right, so let's imagine that you have a tire and you mark the tire with a red circle. Okay, so I have some tire that looks like this. And I'm going to put a red mark right here. So what my cycloid is going to do is going to trace the point on the edge of a rolling circle. All right, so that's what we're going to do. So let's draw this. And I'm going to start with a circle. I may need to make him a little bigger to get my point across because everything's going to be scrunched up inside of him. Okay. All right, so here's my circle and here's my point. All right, that is not right. I have drawn it incorrectly. Okay, now it's right. I apologize. Where is my point? I want my point. I'm trying to figure out where I want my point. I think I want my point here. Okay, so that's where it would be if he had started at 0. Yes. Okay, so if he rolls backwards, he would go to 0. Okay, so the point is he is traveling like this. That is the path of the cycloid. And then he's going to start again. Okay. All right. Now we can talk about it. Okay, so let's find the center of the circle. Here's the center of the circle. And this circle is of radius A. So A is the radius of the circle. So this point right here is the point A times T, zero, okay? All right, so from 0 to T is the distance that the circle has rolled. All right, so let's look at, we're going to put a point, put P right here next to this point. So that's P. And then I want, here's the center of my circle, and I'm going to draw a triangle. All right, so here is P. This is the center of my circle. All right, so my problem is this should not go straight through there. It should be above it. Okay, much better. Okay. Here is the center of my circle. Here is my point from P. So I'm going to go from there to there. Then I have a line here that is going to go to A. And one other line, which I am going to draw by hand, because it's getting on my nerves. Okay. All right, so this is the center. All right, now we can get started. Okay, so now if this circle rolls all the way around, okay, as the circle rolls all the way around, then it's going to cover the distance of the circumference of the circle. So the circumference of the circle is 2 pi times the radius, which is A. So that's what that point is over there. Okay. So now the origin, so OT is the distance of the circle rolled. All right, and that's going to be the length of the arc PT of the angle TCP. All right, so here's T and here's C and there's P, okay? So I'm going to draw this over here on the side. So let me draw over here on the side. So I have a line here. Oh, nope, 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 wrong class. Go back to 253, please. Thank you. And take rid of the line. Okay, thank you. Very good. Okay, so here's the point P. And P is some point XY. And that's that point, little red dot there. Okay, A is the radius of the circle. And so therefore, this is this point C right here. This is the angle T I'm talking about. So there's the angle T. So this is defined by this angle T and how this angle T changes. So if this is the angle little t, which is my parameter, then this distance is A times the sine of t. And this distance up here is A times the cosine of t. And then this point right here, we called Q. And that is the distance A times t and whatever Y value it gets. And the center up here is A times T and its Y value is A. Okay, so now I can see everything. Okay, so T, C, oh, so TCP is right here. So here is TCP. All right, so remember T is somewhere down here. So here's T. All right, and it's at the point AT 0. Okay, so the angle T, so you see it now, TCP. All right, so that's the angle. All right, and the distance rolled is the length of that arc that goes from P to T. So the distance rolled goes from P to T, that's the length of the arc, and that would be right here if it was in this picture. It would be like that. Okay. All right, so now we already know that the distance from here to here is A times T. So the length of O to T is simply A times T. All right, now C, which is equal to AT times A, is the center of the circle. When I let angle TCP just be my parameter T. So T is my parameterization parameter. That is T. Okay. So as I look at this picture, this length over here is AT. But that also has to be this length, which is A sine T. Okay, so if I take any X value, so if I take any X value, I don't think I wrote that right, but AT minus X is simply A sine T. I forgot to put the X in. Yeah, no, I didn't. That's right. So AT minus any X, which is P of XY. So here's P is AT minus X is A sine T. So I have too much here. That's what I have. This should be there because here is my X. So AT, which is this whole length, I subtract off the X value, which is this little piece right here. And that's going to give me this long piece right here, which is A sine T. Now, how about the Y? A minus Y. So A minus Y is this distance. Here's A and there's Y. So A minus Y is this distance. Okay, and that has to equal A cosine T. Okay, So now I get A minus Y is A cosine T. So now all of that together gives me the curve. So X of T is A times T minus A sine T, which most people write as A times T minus sine T. And then Y of T is A minus A cosine T, which most people write as A times 1 minus cosine T. And that is the parameterization for one branch or one particular curve where T goes between 0. Let me see, T starts at 0, so I'm right there. And then T goes all the way around as this gets bigger. Yep, and then when, yep, that's it. I think T goes between 0 and 2 pi, but I have to double check that. Okay, any questions? So this is X of T, and this is Y of T. Okay. All right. Okay. That's the end of that. The next chapter, we're going to use everything we learned from this chapter. Well, the next section, I should say. All right.